Hello, welcome to my session on topology. I'm Sofia Lyakova. I'm from Mathematics Department from Swansea, and I hope you will enjoy this session. In topology, I'm going to introduce you to some new ideas. For example, let's look at these shapes. I'm sure you can give me several reasons why they're different. For example, their perimeters are calculated differently, their areas are calculated differently. Some of them have got straight lines, and the shape on the left has got curved lines. And even if we decide to describe them analytically, the equations of those lines are going to be different. Now, in this lesson, I want you to forget about that and to think about what terminology can we introduce, or how can we shift our thinking to actually start thinking about these shapes as similar. Is there any characteristic that makes them similar as different? And I'm going to give you a clue. So one way to think about them is to how we draw them. For example, the shape on the left-hand side, I can pick up a point, and from any point, actually from any point, exactly any point on that curve, there are two directions to go. I can go either left or right. Well, if I look at the shape in the middle, well, there are some special points. We think of them as special from our experience with geometry. But these four vertices will also have two directions to go from. But in fact, if I pick up a point which is not a vertex, I still gonna have those two directions to go to, or I can come back to that point from two different directions, and that makes them rather similar. And it's the same situation with the triangle on the right-hand side. What other things can be said about them? The other way to think of them as similar is to actually imagine if they're made from a rubber band, which means that, well, think about holding that rubber band on your hands and moving your fingers. You can actually move those shapes. You can easily stretch these corners. Let's use a different color. For example, if I start stretching these points, and at some point, I will end up with a rectangle. Now, if I pick up a point in the middle and just stretch that point, then clearly what I will be doing is making triangle from that shape. On the next slide, we're now going to see formal definition, what we've been doing just now. So, two shapes are called topologically equivalent if they can be twisted or stretched into the same shape without disconnecting any points, that's very important, or making new connections. In other words, we can twist and stretch, but we are not allowed to glue and we are not allowed to cut. From this point of view, these three shapes at the top are topologically equivalent. Now, if we consider these shapes, so what about them? Are they topologically equivalent or not? And the answer here is not. In order to actually reshape the upper one into the lower one, I would need to connect 2 points. So I would need to glue some things. And we can think about what really makes them different from this point of view. So any point in the top shape would have two directions I can travel to or from. And that would be true for infinitely many points up here. For each of those, there are two directions to go from. And in fact, here as well. And that applies to all the points apart from two. Let me use a different color. So these joint points are quite different because I can travel from those points into three different directions and not two. That makes them very different. Now, so they are not topologically equivalent because I would need to glue and cut in order to reshape one shape into another. But when we look at the second row of horizontal shapes, what we can see is that on each of those shapes, there are only 2 points from where there are 3 directions to go to. And that, exactly that, makes them similar. And so all those 3 shapes are actually topologically equivalent. So they are equivalent to each other, but they're actually not equivalent to the original rectangle and the original triangle. Now let's check our understanding. We have two shapes here, two figures. Are they topologically equivalent or not? What do you think? So remember what you can do. Think about them made of a rubber band. Can you shape or twist or stretch shape on the left to make shape on the right, and you're not allowed to glue and you're not allowed to cut. And if you guess that the answer is no, you're quite right. So they're not topologically equivalent. And for example, there will be points on both shapes from which I can go in two different directions, no problems. But there are points on both shapes where there are three directions to go. And in fact, it's only one such point on the left-hand side, but 2 points on the right-hand side. So if I start from the shape on the right, in order to make it topologically equivalent, I would need to cut it somewhere here. And the other way around, if I start from the shape on the left, I would actually need to stretch and to glue. So cutting, and we are not allowed to do that, and gluing, we are also not allowed to do that. So they are not topologically equivalent. Let's look at this too. What do you think? So let's start from this one. So clearly, I can actually reshape it into an oval, no problem. Or we can say an ellipse. So there are no problems. We already know these two are topologically equivalent. Now, if I've got that, yeah, and this would be topologically equivalent, say, to this one. There are no problems. What else can I do? I can actually take this this lead and you know move it on the other side. So if I do that, I will get this. What did we do? Did we stretch anything? Yes. Did we twist? Yes. Did we glue? No, we didn't. Did we cut? No, we didn't. So they are topologically equivalent. Well done for that. So now we'll move to something new. In the previous slides, I used perhaps several different words to when I was talking about, for example, I could have said a shape, a curve, a path, a figure, and so on. In mathematics, all those things need to be clarified. So let's see what we're going to call a curve. A curve in the plane means anything that you can draw without lifting your pen off the paper. So it could be a straight line, it doesn't matter that it's straight. It could be a curved line, it could be lines with loops, and it could be also, we can start and finish at the same place. What I cannot do, if I start drawing, stop, lift my pen off the paper and continue, then I end up not with one curve, but two curves. Also, figures and curves are not identical. For example, we've already seen before that I can draw a triangle by this curve. Yeah, and that's one curve. But I can also do it the other way around. I can do it like that. And that would be a different curve, because for curve, the direction does matter, and it does matter where I started and where I finished. So my starting point here and there. So these are two different curves which define the same figure. Right, another example I've got on the left-hand side, this already has been labeled. For example, I can travel it by this way, D, C, E, B, A, D, F, G, E, D. Yeah, important point is what happens here. So let me repeat what I've done. I've done this. So that we can call a cross, yeah, because I started like that and then I crossed the line. So that's a cross. If I choose a different way, for example, let me draw it in orange. I can go like that. And in that case, you can see there is no cross at C. Let me repeat it here. So that's what I did. So at C, I didn't cross. There is no cross, but it was a touch. And that's what makes it different. So it's important to remember that a curve is not identical to a figure, and more than one curve can describe the same figure. Let us now look at these four curves. Each of them is a curve because I can start and draw, put a dot and actually draw that curve without lifting my pen off the paper. But some other characteristics of these curves are actually quite different. The curves on the left-hand side, I can travel them infinitely many times. I can start at any point I want, and actually I can go in circles. The lower curve is, of course, different because it has got a loop. But equally, I can just travel that curve and I can go in circles infinitely many times. When we look at the shapes on the right-hand side, we cannot do that. And so we think of them as if there is a beginning and there is an end. So from these two end points, there is only one direction to travel, and any other point would have two directions. And this is similar for the curve below. Now, if we split the curves in differently, then we can see that the curves at the top also have some similarities. For example, we can see that there are no loops, and the curves at the bottom do have loops. Why loops are important? Because in the previous example, we did see how a loop can become a cross or it can become a touching point. In mathematics, it's important to define and give some names to certain qualities or characteristics, and this is how these curves would classify. For example, the top left corner would be simple and closed curve. The next one will be not simple because it has a loop, but it is still closed because I can start and finish at the same place. The bottom curves are actually not closed, but the first one is simple, so simple, not closed. And the second one is not simple and also not closed. Let's just summarize what we've done so far. So we've got new ideas. We know when figures can be called topologically equivalent. We know the distinction between a curve and a figure. And we know that some different curves can happen: simple, not simple, and closed, not closed. Interesting things in mathematics happen when we are able to connect several ideas. So let us see if we can see how these ideas we've learned so far can be connected. So what I've got here is a drawing, and it's a shape which can be drawn by a curve, perhaps many different curves, but whether it does matter or not, we'll see in a second. And there are two dots. So there is a point X and there is a point Y. I put them in bold red, but they are just two dots. My first question is, what kind of curve are we talking about? And I hope you would reply to me that it is a closed and simple curve. Closed means that we can start and finish in the same place. Let's see whether we can do that. And simple means that there are no loops. And I think I've just proven to you that this is the case. Now, in mathematics, we often try to simplify things as much as possible without those objects losing important characteristics. So if you think about it, made of a rubber band, how can we simplify it so we don't lose anything important for us? And you perhaps might have already guessed that this form is topologically equivalent to a circle. In fact, any closed simple curve is topologically equivalent to a circle. And that makes our task of looking at points X and Y simpler. So I'm going to put points X and Y here. And now when I reshape this curve into a circle, let's think where our points X and Y are going to be. And point X will be inside, point Y will be outside. The very fact that when we are talking about a closed, simple shape, there is only one inside and there is exactly one outside is important. This fact that every simple closed curve splits the plane in two parts, the inside and the outside, is called a theorem. We may think about it as a very simple and perhaps a trivial fact, but those things sometimes actually very difficult to describe in mathematics, and so it's not just a fact. It's a fact that needed a proof, and that proof needed some new mathematical tools. So I'm not going to tell you how it was done, because if you go to study mathematics at university, you will only be able to dwell into that in your third year. There's a lot of mathematics to do before that, but we can still use it now. It was named after a French mathematician, Camille Jordan, and another way to define, and because of that theorem, all simple closed curves are called Jordan curves. Another way to define the Jordan curve is to say that it is topologically equivalent to a circle. It is simple and closed. My main part of the introduction video is over. Now I think you are ready to start trying problems on the worksheet that I prepared for you. But if you would like to stay for a few more minutes, I'm just going to introduce those problems to you. I think I will try not to give you many hints, but unintentionally, yeah, I might just do that. Okay, so let's see how the first problem looks like. In this task 1.1, you are asked to find all topologically equivalent shapes among the figures on the slide. And remember how to approach these questions. You have to think that they're made from a rubber band and see whether you can stretch them. You're not allowed to glue and you're not allowed to cut. Perhaps you already see straight away that, for example, A is equivalent to L, but there are more shapes on this slide which are equivalent. Second task, task 1.2, deals with exactly the same figures as in task 1.1, and by now you already worked out which of them are topologically equivalent. Now in this task you are asked which of those figures can be drawn by a Jordan curve, which is simple and closed. And those shapes that figures that you found are topologically equivalent. By the way, you may expect that if they can be drawn by a Jordan curve, all of them in the same group would be drawn by a Jordan curve. Here, problem 2 is, let's say, looks like perhaps less abstract, less mathematical in a way. And indeed, it is truly a real-life problem. We've got three neighborhoods, A, B, and C. And we've got three facilities. We've got water, gas, and electricity. We know that it's important for every household to connect to those. And the problem starts with asking you to connect each neighbor to two of those facilities. For example, perhaps neighbor A may be connected to water and gas, and neighbor C may be connected to gas and electricity, and then I want to connect neighbor B with water and electricity. What is not so good on my diagram, these crossings. In real life, it's sometimes very important to actually avoid things being too close to each other, to avoid various accidents. And in these problems, you will be asked to draw diagrams which minimize the amount of crossings. The second part of this problem is more difficult. In the previous case, we tried to connect each neighbor to two facilities. But in this task, and ideally in real life, you ideally would want to be connected to water, gas, and electricity. And so this question is asking whether it's possible to do. And here, perhaps, I may give away a little hint. So once you've done the first task, A, you would know how to connect A, B, and C, each to two of the facilities. I would try to simplify that diagram. Remember, think about that diagram being made from a rubber band, and you'll try to sort of find a simple way so it's still topologically equivalent to your original drawing, but it looks simpler. And then try to add various connections. This problem is not so difficult, but what I want you to do is to refer to the Jordan curve theorem when you're thinking about how to solve it. In the third part, something happens and neighbor C moves away, so there are only two neighbors. And perhaps in this case, maybe that dream of connecting to water, gas, and electricity becomes much more simple. And so the question is about actually in that case, can you do it as a Jordan curve? Please do not miss out my little extra question here because it's going to help you to think about my next problem. Task 3 is about tracing graphs, and I've got 12 graphs for you to start thinking about. For example, if I draw, let me draw this. So, like that, and this. So, it is a closed curve. It's not simple. There is a loop. But can you trace it in such a way that you start at one point and finish in the same point or in a different point? But what is important, you don't take your pen off the paper. So let's see again how I've done it. So I started here. I moved up there, up here. I'm again back to my point. That's okay. And I can do that and I'm done. But is there any other way of doing it? And for example, would it work if I start from this point? And so on. So your task is simple. You need to try to trace these graphs, and you want to travel them without taking your pen off the paper or repeating any edges. So for example, in my example, I repeated one of the corners, one of the vertices, but I didn't travel any side, any edge twice. There are several ways to enjoy these questions, and for example, many students, when I do this class internationally across the world, they find the previous question really fun. I'd like to encourage students to think more analytically and perhaps to analyze what exactly happened. And in the previous example, some graphs can be traveled without taking your pen off the paper or repeating any edges, but others cannot. And these little questions, A, B, C, D, E, F, actually may help you to think what exactly happens. And remember what really makes this different is if you take any point on the diagram, how many directions can it be traveled? Is it just 2? Is it 4? Is it 3? Is it even number of directions or odd? Things like that suddenly do matter. And here is the last problem I prepared for you. It's a famous problem called the Chinese postman problem. Why Chinese? Because it was actually solved by a Chinese mathematician in somewhere in 1950s. It's one of those problems that is highly applicable. Every supermarket chain would need to resolve one of those problems to actually get going and to optimize the way they operate. So what is happening here? This little diagram is a map. Everything starts in depot D, and this postman actually starts from this point. He also needs to come back, and every edge represents a street. So, for example, DC is a street which is 7 meters long, and BC is another street which is 11 meters long. Be careful because, for example, BA looks long, but it's actually only 2 meters. We of course want the postman to deliver all the posts and to come back, and we want to optimize this route. So ideally, what is the shortest route? The question is about finding the shortest route. And theoretically, the shortest route would be just walking each street exactly once and coming back to D. And that is one of those problems you already considered in the previous task. So the idea here is to get all this knowledge that you've learned from task 4 to actually try and solve this problem. I hope you will enjoy it. Right, so this brings us to the end of my introduction. And just to remind you that it's very important that if you need any help, you should get in touch with Further Math Support Program. And if you've got more, if you want extra questions to look at, you can always look at enrichmath.org for more interesting problems. And we would like to hear from you. And I think with every session you receive a feedback form. So please do It's important for us what you say, so please do complete those. Okay, that's it from me, and enjoy working on those problems. A week later, you will get my solutions for this.